In this video, I'm going to be going through my own work solutions to the modelling physics paper from OCR from 2022. If you go to alevelphysicsonline.com, you can also download a full set of work solutions to the paper, as well as see videos for different years and different exam papers as well. So let's begin. Welcome to the modelling physics paper from OCR from 2022. These are my work solutions, which I'm just going to go through. The first one is just really about scalar and vector quantities. Now, looking at the table here, we know that acceleration and displacement are both vector quantities, so it can't be A or B. And then over here, the wavelength is also a scalar quantity, so it's not that. And of course, centripetal force, because it's a force, must be a vector, so D is the correct answer. The absolute uncertainty in repeated readings is going to be equal to half the range. So I've taken the smallest value away from the largest value and divided by 2, which is 0.03 millimeters. So here the answer is B. The next one, we've just got a velocity time graph. I just drew it out here. I kind of sketched it so I could just, I suppose, help explain why I got to this answer. But sometimes just because it doesn't ask you to do any working out doesn't mean that you shouldn't help you actually formulate your answer. So if you've got a velocity time graph, the gradient is going to be equal to the acceleration, and the area under the line is going to be equal to the displacement. And therefore, looking at the list over here, A is the correct answer. For this one, we've got the weight of the object is 1.2, so that's going to be acting down. There's an upthrust of 0.8 over here, and then we've also got a drag force over here. So we can see that if the drag force is acting upwards, that's because the velocity of this object must be down, so the velocity is down. And if we look at the forces, we've got a total of 1.2 down and 1.4 up, so the resultant force is going to be upwards. And that means, even though it's moving down, the resultant force is up, and that means it's going to be slowing down or decelerating. So the answer for this is C. And I think just by adding a bit more to the diagram, identifying which forces are which, that will really help you get to the correct answer. It says that the object here in question 5 is in equilibrium, and that means there must be no resultant force on it. So you can see, effectively we've got a couple here, so we've got 10 newtons up and 10 newtons down, and also there's going to be a force which must be equal in size to 5.6 newtons, but it must be acting in the opposite direction. So from P, the force must be acting something like that. And therefore here, B is the correct answer. So it's an equal size force in the opposite direction. And it's the only one of these that has an equal size force in the opposite direction. Number 6, I think this question was quite tricky for a lot of people. So we've got two objects, and I've got them in Lego here. They collide, and initially in the vertical, so let's say that this is the vertical direction and that's the horizontal direction. In the vertical direction, because this is moving to the right, the momentum is 0. After they collide, they're going to move off like this, and there's going to be a vertical component of momentum of this and a vertical component of momentum of that. But those two vertical components of momentum also add up to 0. Now that's going to be equal to mv1 sine 60 plus 4m v2 sine 30. Okay, because if that's 90 degrees and that's 60, that must be 30. So we can then basically say from this, because the m's cancel, v1 over v2 is 4 sine 30 over sine 60. Whack the numbers in your calculator. This gives a number of 2.31, which is A. The increase in thermal energy is equal to mc delta theta, and of course the power is the energy transferred per unit time. And that means if we divide both of the sides here by t, the change in energy over time is equal to mc delta theta over delta t. But of course this is just the power, and this is equal to g, which is the gradient of that straight line graph. So the power is equal to mcg, so the specific heat capacity is equal to the power divided by mg. So that was my approach to kind of work this out, and then I looked down here to see which of these it might be, and the correct answer was D. With number 8, I just went through the statements and ticked the correct ones. So a gas is mostly empty space is true. And also the gas particles spend more time between collisions than during collisions. So those are both true. There are always forces between the gas particles is an incorrect statement. So really, looking at these, 1 and 2 are correct. And once I did my ticks and crosses, I then looked at which of these was a suitable statement, and A is a suitable one. So you need to know about the assumptions for the kinetic theory model of gases. You just need to know them off by heart, and that makes questions like that pretty straightforward. Now, I think I took a different approach to the way that the examiner's report mentioned was probably a better, quicker method. My approach was to say that the kinetic energy of an individual particle is going to be equal to 3/2 kT, and I could use that then to work out the temperature, and then I just inserted that into the ideal gas equation and rearranged to say that the volume is equal to nRm c² over P times 3K. I put the numbers in up here and I just identified which number was which from this, and that gave me a volume of 0.0236 or 2.4 times 10 to the minus 2 meters cubed. That seemed like quite a lot of work in terms of like what we had to do to actually, I suppose, manipulate the equations up here. There's another way that you can do it that the examiner's report mentioned, but I thought that seemed absolutely fine. Again, quite a lot of work for 1 mark. We then have a mass attached to a spring, which is oscillating. Which row describes the energy when the mass is at its lowest point? So the spring is extended, the mass has got to the bottom, and it's going to have the greatest elastic potential energy at that point. It's also going to have the minimum gravitational potential energy, and so looking at which were the incorrect ones, only B had 2 correct statements here, and I guess really to confirm that, the kinetic energy at the end when it's not moving is going to be 0, and therefore B was the correct row. This one caught out quite a few people. I think the reason for that might be that people assume that was gravitational potential energy. So acceleration, gravitational field strength have the units, or can be expressed in meters per second squared. Angular frequency and angular velocity both have the units of radians per second, but gravitational potential is the energy per unit mass, so it's joules per kilogram, whereas kinetic energy is joules, so they've got different units. And of course, impulse and momentum, kilogram meters per second or newton seconds. So here, the ones that don't have the same or equivalent units are these two, so the answer is C. I know that quite a few students found that tricky. For number 12, we've got an electron absorbing a photon, so that means the arrow must be going up to represent the electron moving to a higher energy level. And also, if it's got the shortest wavelength, because E is equal to hc over lambda, when you've got a shorter wavelength, we've got a greater energy of that photon. So we're going to have the biggest transition, which is going from Z to X, and therefore the answer is A. Number 13 was also quite, I thought quite a nice question, but quite tricky for 1 mark as a multiple choice. So first of all, we've got the speed of the star is 0.16 c, and therefore 0.16 is equal to the change in wavelength over the original wavelength. So we can use that to work out the change in wavelength, and we just add that onto the original wavelength of 486 to get the final wavelength, lambda 2, of that redshifted light. I then used the equation that says n lambda equals d sine theta, and if you rearrange this, you can say that n over d is equal to sine theta over lambda. Now, of course, n and d are both going to be the same. We've got the same order, and we've got the same spacing between the diffraction gratings, and therefore sine theta over lambda is a constant. So sine 30 over 486 is going to be the same as sine of the new angle theta divided by the new wavelength. And that means you can then solve for theta being equal to 35.45. So here, the answer is D. I would say, initially, you know it's not going to be the same angle, and it's not going to be something smaller. It must be a bigger angle. So it's really between these two, and when you actually do the calculation, you find the answer is D. So I thought that was a lovely question, but actually quite difficult as a multiple choice question. the recessional velocity is equal to the Hubble constant times the distance, and also the age of the universe is equal to 1 over the Hubble's constant. So that means the time is equal to the distance divided by the recessional velocity of that galaxy. And that then gives us the equation, which is this one over here. So C is the correct answer. And finally, the fact that I guess everywhere we look we seem to see galaxies approximately spread evenly throughout the whole universe in all directions is to do with the cosmological principle. The fact that the universe is homogeneous and isotropic. So that's what that observation supports. So the answer for that one is B. That was the end of the warm-up part of the paper, the multiple choice questions. Again, don't forget, if there's anything that you're not sure about, make sure at the end of the exam as you're going and checking through your answers, at the very least you can't leave any blanks, at the very least guess for all of your answers at the end of that exam. I think students tended to do quite well with question 16. The first one is quite clear that people could remember doing a similar experiment beforehand. Basically, you've got the cord, you hang some masses on it, so there are forces being applied. You then measure the extension, and then if you plot the extension versus the weight on a graph, you can then use a gradient to calculate the force constant for the straight line part of that. So again, just setting stuff out, and of course you can use bullet points to help organise your answer. We then have the cord here that's pulled back, lots of information here, and the first question asks you to use the graph to show that the elastic potential energy is about 1 joule. So the elastic potential energy is going to be equal to half kx squared. Now when it's pulled back 10 centimetres, the extension is equal to 6.0 centimetres. We've got the spring constant given to us on that previous page, and then we've got our extension in metres, which is squared, giving an answer of 0.90 joules, which is about 1 joule. So because it's a show question, you need to give your answer to more significant figures than the number you're trying to show over here. We then want to look at how this is related to the maximum speed of the ball that actually leaves the catapult. And of course, we're going to assume that all of that elastic potential energy is transferred to the kinetic energy store, which is equal to half mv squared, to find that it leaves at 7.746 metres per second, which is about 8 metres per second. So fairly straightforward kind of calculations there. We then have a beautiful bit of suvat. My approach was to think about the vertical component of velocity. It falls through a height of 1.5 metres. The vertical component is initially 0, and it's accelerating at 9.81 metres per second squared. So we can use this equation here to find that t is equal to root 2s over a, put the numbers in, and we know that it falls for about 0.553 seconds. But of course, for the time it's falling, it's also going to be moving horizontally, and the horizontal displacement is going to be equal to its velocity that we calculated in part 2 times this time. So it goes 4.28 or 4.3 metres to two significant figures like our raw data. Of course, that's in an ideal real-world scenario, but the actual distance would probably be smaller than this, because not all of the energy stored in the elastic band in that cord will have been transferred to the kinetic energy of the ball, and therefore the horizontal velocity is actually smaller than this value. So if that's smaller, that means this is going to be smaller as well. So yeah, just a comment on how this is related to real life. For this, it says an electric engine. Now, unfortunately, I don't actually have a Lego model of a train that's electric, so we're going to have to imagine that this kind of old-style train is the electric engine. And we need to show that the time taken for the engine to reach its maximum speed is about a minute. So, it says in the question the power output, and it also talks about the maximum kinetic energy, which is going to be 15 megajoules. Now, of course, if power is energy over time, time is equal to the energy over the power, and the time it takes to get to this maximum kinetic energy is going to be equal to this 15 megajoules divided by 280 kilowatts, which is 54 seconds, which is approximately 1 minute. For part B, I think generally answered quite well. It says here that the engine is moving at a constant maximum speed. So that means it's going to be in equilibrium, which means the force to the left and the force to the right are equal in size, but opposite direction, and also the weight is equal to the normal contact force. This bit was done pretty well. The weight of this engine is going to be equal to its mass of 17,000 times 9.81, which is about 167 kilonewtons. So that means also the normal contact force is going to be the same value of 167 kilonewtons. The force forwards was maybe a little bit more tricky. We know that power equals force times velocity, so the force is equal to the power divided by the velocity. So it's this power, 280 kilowatts, divided by 42 meters per second to get the forwards force as 6,670 or 6,700 newtons, to, I guess, two significant figures. So that force to the left is 6,700 newtons, the same size as the force to the right. Okay, we then have, again, more information repeated, so that's quite good actually that they've given you that information again. We've got the distance when the driver sees the obstruction ahead. The engine is switched off and the brakes are applied. So, show with the help of calculations that the engine will stop before reaching the obstruction. So we need to actually calculate the total stopping distance. Now that's the thinking distance, which is the distance that the engine travels after the driver has seen the obstruction. So they're travelling at 42 meters per second and their reaction time is 0.40. So the distance it travels is 16.8 meters before the brakes are applied. And then the work done by the brakes was going to be equal to the force of the brakes times the distance that they're acting, and that's equal to the initial kinetic energy of that engine. So S is going to be the kinetic energy divided by the force, or 15 megajoules divided by 120 kilonewtons, which is 125 meters. So the total stopping distance is this 16.8 plus 125, which is 141.8. And then to really get the last mark, we need to compare this value here with the 167 meters given in the question. And we can see that that's less than 167, and therefore it will stop in time. So, a lovely question about trains. Maybe I need to get myself some more Lego trains if I come up to similar questions in the future with electric engines. Question 18 is quite a tricky question in many ways. We've got this tent here, and there's a certain amount of air that hits that side in 3 seconds. We want to work out the mass of the air in this 3-second time interval. Now my approach for that was to really consider the volume of air which is going to be hitting that side in those 3 seconds. And if you know the volume and you know the density of air, which is given to us as 1.2, we could work out the mass of that air. Now, in terms of the volume of air that hits it, we've got to sort of consider this side of the tent, and there's going to be this volume of air that passes into that space in 3 seconds. So if it's 12 meters per second and it acts for 3 seconds, that's going to be 36 meters of air that kind of hit this side of the tent. Now we can multiply that 36 by the area of that side of the tent, which is 6 times 1.9. And so the volume of air that hits this is 410.4 meters cubed. The mass then is going to be this volume times 1.2, which is then 492.48, which is approximately 490 kilograms of air hitting the side of that tent. The next one, again, many students found this quite tricky. So we've got the wind, it hits the side of the tent, and then it's going to move off to the side. Now, in the direction of the tent, the change in momentum is going to be equal to the mass times the change in velocity. We were given the mass, or we've worked it out in that previous thing, and the mass times the change in velocity is equal to this mass of air times 12 minus 0, because it was going at 12, and now after it's gone to the side in this direction, the velocity is 0. So the change in momentum is 5,910 kilograms metres second to the minus 1. But from Newton's second law, that force is going to be proportional to the rate of change of momentum, and it changes this momentum over a time of 3 seconds, and therefore the force is just going to be equal to 2.0 times 10 to the 3 newtons. Tricky question, followed up by another tricky question where I think very few students actually managed to get 6. The first thing, which isn't intuitive really, is that basically when this air is hitting the side, if it was going faster, you'd have a greater mass per unit time, and also we'd have a greater change in velocity. Now, if it goes from 20 to 40, we're going to have double the mass of air hitting the side of the tent every second, and double the change in velocity. So we're doubling delta V, and we're doubling m delta over delta t. And that means the force is actually going to increase by a factor of 4. And that's something that I think lots of students didn't quite realise. So if we're going to have 4 times the force, that means the area of the guy ropes, so that's the area of the guy ropes, must increase by a factor of 4. And you could do that by doubling the diameter. The other thing you could do is modify the shape of the tent so it's more streamlined. I mean, people don't tend to use tents like this. They tend to allow the wind to actually move over the top of them. And if you've got something more streamlined, there's going to be a smaller change in momentum, so a smaller force is needed. And of course, the other thing you could also alter, and we've got, going back to the diagram over here, was the angle between the guy ropes and the ground could be reduced. So you have the guy ropes further out. And if you do that, we're decreasing the angle between the guy rope and the ground, and that means it reduces the component of tension perpendicular to the ground, and therefore the tension in those would decrease. So, a few ideas, but I thought that was a really, really difficult, challenging question. When we have a phase change going from a liquid to a gas, although it's a constant temperature, so the kinetic energy of the particles is the same, it's going to be the potential energy that increases, and therefore the internal energy has also increased. This one over here, pretty straightforward in terms of rearranging the ideal gas equation to find the number of moles. That's just equal to this pressure times this volume divided by the molar gas constant times the temperature in Kelvin. That's where a few people made mistakes. Always add 273 onto the values in degrees Celsius. So this is about 609.8, which is about 600 moles. Then into a little bit of chemistry. The total mass is going to be equal to the number of moles times the molar mass. Multiply the two together to get 17 kilograms. And it says here that volume of nitrogen cannot be changed. Now, of course, from this equation over here, we know that PV over T, and that means you can either reduce the pressure or you could increase the temperature. So that's two ways to reduce the rate that mass of nitrogen can be used. I thought this was a little bit tricky, and I think the reason is because the air is at 0 degrees. So at 0 degrees, we have both a gas turning into a liquid and then that liquid turning into a solid. So that's what we have over here. So obviously the energy transferred to the liquid nitrogen is going to be the same as the energy transferred from the water vapour. So I've got my kind of shorthand here. So we've got the mass of the nitrogen times LVN. This is what we're trying to find out, the specific latent heat of vaporization of the nitrogen. And that's going to be equal to the mass of the water times the latent heat of fusion of water plus the mass of that water times the latent heat of vaporization of the water. And of course, that's happening at 0 degrees, and so is that. So there's no E equals mc delta theta kind of specific heat capacity that we need to consider. So we can rearrange this to say that the mass of the water times this plus this divided by 17.07, the mass of nitrogen we worked out in the previous part of the question. This gives us the energy per kilogram for that phase change to be 197.495, so 2.0 times 10 to the 5 joules per kilogram. So I thought this is quite tricky, and I think it's really that you had to have the energy transferred from the water vapour for both phase changes within this calculation. So that was a little kind of sort of tricky thing to see. For number 20, we know that the angular frequency, because that's radians per second, will have the unit, the SI base unit of seconds to the -1. So omega squared is seconds to the -2. And of course, the displacement x is going to be in meters. So omega squared x is going to be seconds to the -2 times meters. And acceleration is meters seconds to the -2. So this and this are the same. Right, a question about YouTube. The change in pressure is equal to rho g delta h. So we've got the density of the liquid is 1000, g is 9.81, and the height between this point and this point is equal to 2x, or indeed it's given as 10 centimetres. So that's where some people just thought that the height is just equal to 5 centimetres. It's not. It's 10 centimetres between the two different heights of the liquid, and that's why we multiply that by 2 times 5 times 10 to the -3 to give the change in pressure as 980 pascals. For this part, again, we know the answer we're going to get is going to be a second. So it says the acceleration is 2 rho g a over m times x. And also, it says in the previous part of the question how this acceleration is minus omega squared x. So I equated this and this together to say that this is equal to minus omega squared x. Of course, the negative signs cancel, the x's cancel, and then you can find omega is equal to the square root of 2 rho g a over m. Put the numbers in from the question to find that omega is 6.14 seconds to the -1. And then, of course, the time period is going to be 2 pi over omega, because omega is 2 pi over the time period. So 2 pi divided by this number is 1.023 seconds, which is approximately 1 second. So that was my approach to that. I maybe found it a bit difficult to sort of fit everything in that space. The next one, we know, of course, that the time period is about a second. So I said, well, one cycle is going to be, well, if that's 0, and that's maybe 1 second, and that's 2 seconds, we're going to have one cycle here and another cycle there. But of course, it's also lightly damped motion. So I just kind of put this construction line showing how we have this exponential decay of the maximum amplitude of each cycle. And therefore, I kind of just sketched in my wave cycles like this, making sure that the time period is constant each time. It's just the displacement, or the maximum displacement of each cycle, which is decreasing by the same proportion each time. And then, of course, you have a question, because it's quite a synoptic kind of paper where they involve lots of different bits of physics together. We've got a driving frequency of a hertz, which is very similar to the natural frequency of this system. And that means you have resonance occurring. And that causes these large amplitude vibrations of that water up and down inside that U-tube. A nebula will collapse because of the gravitational force of attraction of everything, attracting everything else within it. We then need to look at the volume of that. So that's going to be equal to 4/3 pi r cubed. And the radius of this, well, it's given us the diameter here, so I've divided that by 2 to get the radius. I've then converted from parsecs into meters, and I've cubed that to find that this is 4.089 times 10 to the 51, or about 4.1 times 10 to the 51 meters cubed. That's an enormous volume. We then need to calculate the total kinetic energy of the gas and dust particles within that. Now, the kinetic energy of one particle is going to be equal to 3/2 kT. So we've got our temperature given to us in Kelvin, luckily, and that means we can look at the energy per particle. And of course, if we know the energy per particle, we can multiply that by the volume of the nebula multiplied by the number of particles per cubic meter, which is given to us up here. So we're just going to multiply this by that to find that this is equal to 2.1 times 10 to the 43 joules, which is a pretty big number. So I think generally people found that question okay and managed to have a go at that. I don't know why there's a random kind of bit of pen there, so ignore that. Okay, calculate the ratio of the mass of the nebula to the mass of the Sun. Now, the density is equal to the mass over volume, so the mass is equal to the density times the volume. And if we're going to assume that it's got a similar composition, it's going to have a similar density, so the mass will be proportional to the volume, which will be proportional to d cubed. So the mass of nebula X divided by the mass of the Sun's nebula is equal to dx cubed over the diameter of the Sun's nebula cubed. So that's 6.4 divided by 3. I've left them both in parsecs because they cancel. That's cubed, and that's equal to 9.71. So the ratio of the mass of that other nebula to the nebula that made our Sun is 9.7. After a long time, nebula X will form a stable star. Describe the eventual evolution of this star. So it's something which is much heavier than our Sun, and as the fuel runs out, this star evolves into a super red giant, and because the mass of the core is greater than the Chandrasekhar limit, it will supernova because it's so much bigger than our Sun, and that means it's going to leave either a neutron star or a black hole behind after it's supernovaed. 22 is really starting with a question about uncertainty, but in the context of measurements in space. Now, of course, if we're trying to find R, we need to know L and we need to know T, but here T is raised to the power 4. So any percentage uncertainty in T is going to have 4 times the significance of any percentage uncertainty in L, and therefore you need to attempt to measure T more precisely. For the next question, we've got, again, an unknown formula you've never seen beforehand, but we've got a graph where we've got a log-log plot, which is a bit of a clue for the first stage. What I did was I took this equation, I took the natural log of both sides, and that means, because we're plotting this on the y-axis and this on the x-axis, the gradient is equal to b, this constant. So we can determine b just by calculating the gradient of this line. So I just drew in my line of best fit, I drew a large triangle, I then calculated it very clearly, and the value for b is about 3.67. So this value can be used later in your explanation. So here's my HR diagram, and also we know, of course, that the luminosity is going to be related to temperature. So when something is much hotter, it's going to be more luminous. But how's that related to the mass? Well, we know that if something has maybe got a luminosity 8,000 times greater than something maybe like our Sun, it means that the mass is about 8.3 times greater. But if it's much more luminous, it's going to be losing mass at a much greater rate. And that means they must have a much smaller lifespan. So effectively, hotter stars are more luminous. That means they're giving out more energy per second, they're burning through their mass quicker, and therefore they have a shorter lifetime. Hopefully I kind of got that explanation down there. So to kind of, I guess, really link the second part to the explanation, if you showed some kind of calculation using your value of b, that would help kind of help with your explanation about the lifespans of these hotter stars, or how that compares to the lifespans of cooler stars. And 23, I think, is the last question. The first one, pretty straightforward marks. It comes up, I think it's come up quite a few times previously, where you can equate the centripetal force to the gravitational force of attraction, substituting our value for v to find that t squared is equal to 4 pi r cubed over gm, and therefore t squared is proportional to r cubed. So that's just a relatively straightforward standard derivation. The next question, we've got some data here, and we need to use Kepler's third law. So Kepler's third law is this. And of course, if we know that t squared is proportional to r cubed, then t squared over r cubed is going to be equal to a constant value. So if we consider the Earth and the satellite, we can say that the radius of the satellite is going to be equal to the radius of the Earth times the cube root of the period of the Earth squared over the period of the satellite squared. And when you put the numbers in, we find that the distance is 8.9 times 10 to the 11 metres. So that's going to be the mean orbital distance of the satellite from the Sun. using Kepler's third law, which is why we had to do this for the first part of the question. We then have something where we can look at the change in kinetic energy is going to be equal to the same size as the change in the gravitational potential energy, which is going to be gm over delta r. And here we've got the two different values of r. And when you put the numbers in, so we've got our big G, mass of the satellite, mass of the sun, and also the two different points that were mentioned. So 4.2 times 10 to the 10 and 1.37 times 10 to the 11. This means change in gravitational potential energy, which is the same as the change in kinetic energy, is 4.6 times 10 to the 10 joules. And finally, the last one, a bit of a sort of higher demand kind of question. Why the total energy of the satellite in orbit around the sun is not the same as the total energy of the satellite during its launch from the surface of the Earth. Well, effectively, when that satellite was on the Earth, it was in the kind of gravitational well of the Earth, and therefore work had to be done to get the satellite away from the Earth, through the atmosphere, and then into orbit just around the sun. Has that explained it? Hopefully it has. Anyway, those were my kind of work solutions. Hopefully they helped you, having already done the paper yourself, having worked through this. And if there's anything that you didn't understand from the mark scheme, hopefully some of this has helped. But I really hope your real exam goes well. Don't forget, of course, I do have other videos where I go through the other papers that OCR has done, as well as modelling physics from other years as well as 2022. Thank you so much for watching.